Now, here is a typical graph you may see in an exam question based on this type of reaction. First thing to do, check what the x and y axis are. The x-axis is time, measured in seconds. The y-axis is the volume of gas produced. Now, you may have to plot a graph from a table, or you may be given a graph, fully plotted. You may be given a graph with a line of best fit on it. But it's important to remember that in chemistry and in other sciences, a line of best fit does not have to be a straight line. It can be a smooth curve. And in this example, it definitely is meant to be a smooth curve. And you need to be able to draw smooth curves. Now, I've just rotated the paper a bit to try and show you how I draw smooth curves. I'd like to use my elbow as the pivot, like as the point of a compass needle, and that helps to get a smoother curve. So, something like this. And if I can't do it in one move, carefully find position and then... There we go. Having got your completed graph, there's a few things you can say from it. For example, the reaction starts off steep, or the graph starts off steep, gradually gets less steep, and then flattens out. What does this tell us? Well, firstly, it tells us that the reaction is fastest at the start, and as the particles gradually get used up so that the concentration of my acid is getting more and more dilute, there are fewer particles in the same volume, so there are fewer collisions per second, which is why the graph gets less steep. And eventually, when the graph is horizontal, the reaction has finished. It's important when answering an exam question to read it carefully. Does it simply say, describe the shape of the graph? In which case you can just say it starts off steep and gradually gets less steep until it flattens out. And you may have to quote numbers, like, for example, after 60 seconds, the reaction is flat. Or do you have to explain the shape of the graph? If explanation is needed, then you have to start talking about particles and collisions. And you need to be very precise. You need to say the number of particles in the same volume is decreasing. Therefore, the number of collisions per second is decreasing. Don't forget in the same volume, and don't forget per second. Now, there are two new types of calculation you might expect to be able to carry out from the graph and the data it provides you with. So, for example, you might be asked, what is the average rate of reaction over the first 60 seconds? And to work out the average rate, you note the time, 60 seconds, and then you read across to the y-axis, and that is 31 centimeters cubed. That means that the average rate in that first 60 seconds is the volume of gas produced, 31 centimeters cubed, divided by the time taken, which was 60 seconds. 31 divided by 60, we need a calculator to do that. 31 divided by 60 equals 0.516666, let's call it 517, and the units, the volume of gas is centimeters cubed, the time is second, so it's centimeters cubed per second. So that's the average rate in the first 60 seconds. Another possible question is for you to be asked to say what the rate is at a particular time during the experiment. So, for example, what is the rate of reaction at 20 seconds? Not the average rate, but what is the rate at that very instant? And to do that, you have to draw a tangent to the graph. Now, a tangent is a line that just touches the graph, or the curve, but doesn't cross it. So I'm going to draw a tangent that touches it at 20 seconds. The rate of the reaction will be the gradient of this tangent. So, how are we going to work out the gradient? We need to know how much it's gone up, the change in y, divided by how much it's gone across, the change in x. To do that, I need to draw a triangle. Now, I'm going to draw a triangle. It doesn't matter where you do it, in fact, so long as you note where it meets the straight line, not the graph, but the straight line, the tangent that you've drawn. So, it's gone from there to there in terms of the x, and it's gone from there to there in terms of the y. Now, the gradient, you may have learnt in maths, is the second y reading minus the first y reading divided by the second x reading minus the first x reading. And this is probably the easiest way to do it. So my second y reading on the tangent, where I've drawn my triangle, is 31, roughly. And my first y reading, because I've drawn it on this line there, is 10. My second x reading, because I've drawn it on that line, is 40, minus my first x reading, that's 10, 9 is 8 there. So I get 21 over 32. I put that into my calculator. 21 divided by 32 equals 0.656, 0.656. I'll give it to three significant figures. And again, the units are centimetres cubed per second. So that is how you work out the rate at a particular point. The change in y, we worked out, was 31 minus 10, which is 21 centimetres cubed. The change in x was from 8 to 40, which is 32 seconds. And that's how we got our rate at that particular instant, at 20 seconds. So you could be asked either of those, the average rate or the rate at a particular instant. Now here is a very different graph we've been given. What is it this time? First of all, look at the axes. They will tell you this in the question, but it's still worth looking at the labels. The x-axis is the concentration of hydrochloric acid, measured in moles per decimetre cubed. Don't worry about that too much at the moment. The rate of the reaction, measured in centimetres cubed per second. And in this graph, they're showing not one experiment, but a series of experiments. You've repeated the experiment with 1, 2, 3, 4, 5, 6 different concentrations of hydrochloric acid. And you've measured the rate of reaction, or calculated the rate of reaction for each of the 6 values, and plotted them on the graph. Very likely they'll plot these for you. And then they might ask you to complete the graph by drawing a line of best fit. Now this time, it looks very much like it's definitely a straight line. If it's a straight line, use a ruler. It happens to be a straight line going through the origin, north. Sorry about that. So, what can we say about this graph? Well, two things. One is, if it's a straight line going through the origin, then the rate is directly proportional to the concentration. That means if you double concentration, you double rate. People like this phrase, directly proportional. But for something to be directly proportional, it needs to be two things. It needs to be a straight line, and it must go through the origin. If it's just a straight line but doesn't go through 0, 0, it's not directly proportional. But in this case, it very clearly is. However, as often is the case, there is an anomalous result. At a concentration of 2 moles per decimetre cubed of hydrochloric acid, the result is lower than it should be. How can we explain this anomalous result? Well, it's lower than it should be. So it's just possible that when the reaction was started, and remember I have to put the bung on, add the chemical, and start the stopwatch at the same time, it could be that the stopwatch was started before the bung was fully on the reaction mixture, so some of the gas produced escaped. This would mean that over however long you're timing the experiment for, there'd be less gas in the gas syringe or measuring cylinder, and so you'd get a lower result for your rate of reaction. And consequently, this result is lower than it should be. So, you are often expected to try and explain why a result is different or why it's anomalous. Try and be as precise as you can. Don't just say they timed it wrong. Try and think of what might have happened. Some gas may have escaped, or the temperature was lower than it should have been. Don't just say it was the wrong temperature.